The following theorem will enable us to prove the well-known Pythagorean theorem. Theorem 5.4.1. The altitude drawn to the hypotenuse of a right triangle separates the right triangle into two right triangles that are similar to each other and to the original right triangle. Theorem 5.4.1 is illustrated by figure 5.18, in which the right triangle, triangle ABC, has its right angle at vertex C, so that segment CD is the altitude to hypotenuse segment AB. The smaller triangles are shown in figure 5.18b and C, and the original triangle is shown in figure 5.18d. Note the matching arcs indicating congruent angles. In figure 5.18a, segment AD and segment DB are known as segments, parts, of the hypotenuse segment AB. Furthermore, segment AD is the segment of the hypotenuse adjacent to, next to, leg segment AC, and segment BD is the segment of the hypotenuse adjacent to leg segment BC. Theorem 5.4.2. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Lemma 5.4.3. The length of each leg of a right triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. Theorem 5.4.4. Pythagorean theorem. The square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of the legs. Given triangle RST with right angle S in figure 5.23, find A. Length RT if length RS equals 3 and length ST equals 4. Solution. With right angle S, the hypotenuse is segment RT. Then, length RT equals C, length of RS equals A, and length of ST equals B. A squared plus B squared equals C squared gives us 3 squared plus 4 squared equals C squared. 9 plus 16 equals C squared gives us 25 equals C squared, or C squared equals 25, which becomes square root of C squared equals square root of 25. C equals 5, length of RT equals 5. Given triangle RST with right angle S in figure 5.23, find B. Length of RT if length RS equals 4 and length ST equals 6. Solution. With right angle S, the hypotenuse is segment RT. Then, length RT equals C, length of RS equals A, and length of ST equals B. B. A squared plus B squared equals C squared becomes 4 squared plus 6 squared equals C squared. 16 plus 36 equals C squared becomes 52 equals C squared, or C squared equals 52, which becomes the square root of C squared equals the square root of 52. C equals the square root of the product 4 times 13. Simplify the radical. C equals 2 square roots of 13. Length RT equals 2 square roots of 13, which is approximately equal to 7.21. Given triangle RST with right angle S in figure 5.23, find C. Length RS if length ST equals 12 and length RT equals 13. Solution. With right angle S, the hypotenuse is segment RT. Then, length RT equals C, length of RS equals A, and length of ST equals B. C. A squared plus B squared equals C squared becomes A squared plus 12 squared equals 13 squared. A squared plus 144 equals 169. Minus 144 minus 144. Subtract 144 from both sides. A squared equals 25, which becomes the square root of A squared equals the square root of 25. A equals 5. Length RS equals 5. Given triangle RST with right angle S in figure 5.23, find D. Length ST if length RS equals 6 and length RT equals 9. Solution. With right angle S, the hypotenuse is segment RT. Then, length RT equals C, length of RS equals A, and length of ST equals B. D. A squared plus B squared equals C squared becomes 6 squared plus B squared equals 9 squared. 36 plus B squared equals 81. Minus 36 minus 36. Subtract 36 from both sides. B squared equals 45, which becomes the square root of B squared equals the square root of 45. B equals the square root of the product 9 times 5, which equals 3 square root of 5. Simplify the radical. Length ST equals 3 square root of 5, which is approximately equal to 6.71. Theorem 5.4.5. Converse of Pythagorean theorem. If A, B, and C are the lengths of the three sides of a triangle, with C the length of the longest side, and if C squared equals A squared plus B squared, then the triangle is a right triangle with the right angle opposite the side of length C. Theorem 5.4.6. If the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the triangles are congruent. HL. Our work with the Pythagorean theorem would be incomplete if we did not address two issues. The first, Pythagorean triples, involves natural or counting numbers as possible choices of A, B, and C. The second leads to the classification of triangles according to the lengths of their sides. Definition. A Pythagorean triple is a set of three natural numbers, parentheses A, B, C, parentheses, for which A squared plus B squared equals C squared. Three sets of Pythagorean triples encountered in this section are 3, 4, 5, 5, 12, 13, and 8, 15, 17. These numbers will always fit the sides of a right triangle. Natural number multiples of any of these triples will also constitute Pythagorean triples. For example, doubling 3, 4, 5 yields 6, 8, 10, which is also a Pythagorean triple. In figure 5.29, the triangles are similar by side-side-side similarity. The Pythagorean triple 3, 4, 5 also leads to 9, 12, 15, 12, 16, 20, and 15, 20, 25. The Pythagorean triple 5, 12, 13 leads to triples such as 10, 24, 26, and 15, 36, 39. Basic Pythagorean triples that are used less frequently include 7, 24, 25, 9, 40, 41, and 20, 21, 29. Pythagorean triples can be generated by using select formulas, where P and Q are natural numbers and P is greater than Q. One formula uses 2pq for the length of one leg, p squared minus q squared for the length of the other leg, and p squared plus q squared for the length of the hypotenuse. See figure 5.30. Table 5.1 lists some Pythagorean triples corresponding to choices for P and Q. The triples printed in boldface type are basic triples, also known as primitive triples. In application, knowledge of the primitive triples and their multiples will save you considerable time and effort. In the final column, the resulting triple is provided in the order from A, small, to C, large. The converse of the Pythagorean theorem allows us to recognize a right triangle by knowing the lengths of its sides. A variation on the converse allows us to determine whether a triangle is acute or obtuse. Theorem 5.4.7. Let A, B, and C represent the lengths of the three sides of a triangle, with C the length of the longest side. Number 1. If C squared is greater than A squared plus B squared, then the triangle is obtuse, and the obtuse angle lies opposite the side of length C. Number 2. If C squared is less than A squared plus B squared, then the triangle is acute. Determine the type of triangle represented if the lengths of its sides are as follows. A. 4, 5, 7. Solution. A. Choosing c equal to 7, we have 7 squared, question mark, 4 squared plus 5 squared. 49, question mark, 16 plus 25. 49 is greater than 41. C squared is greater than a squared plus b squared. The triangle is obtuse. Determine the type of triangle represented if the lengths of its sides are as follows. B. 6, 7, 8. Solution. Choosing c equals 8, we have 8 squared, question mark, 6 squared plus 7 squared. 64, question mark, 36 plus 49. 64 is less than 85. C squared is less than a squared plus b squared. The triangle is acute. Determine the type of triangle represented if the lengths of its sides are as follows. C. 9, 12, 15. Solution. C. Choosing c equal to 15, we have 15 squared, question mark, 9 squared plus 12 squared. 225, question mark, 81 plus 144. 225 equals 225. C squared equals a squared plus b squared. The triangle is a right triangle. Determine the type of triangle represented if the lengths of its sides are as follows. D. 3, 4, 9. Solution. D. Because 9 is greater than 3 plus 4, no triangle is possible. Remember that the sum of the lengths of two sides of a triangle must be greater than the length of the third side. No triangle is possible.